Dear students, we are going to see Unit 4 today, that is about process and operating system. And I have divided the Unit 4 into two parts, part 1 as well as part 2. So in part 1, we are going to discuss about multiple tasks and processes and also the topic multi-rate systems. In part 2, we are going to discuss about preemptive real-time operating system and inter-process communication. So mainly I'm going to focus only on the inter-process communication since preemptive real-time operating system is given as an assignment for you. So under part 1, we have multiple tasks and multiple processes. So before knowing about multiple tasks and multiple processes, we have to know what is task and process in a system. Okay, so task is a piece of work that should be done within a period of time, or you can say task is a work that should be done within a particular deadline. If the task in a system is missed within a particular deadline, that means the entire process will get collapsed. For example, you know the real-time applications. In real-time application, task, it plays an important role. So each task, it has its own deadline. Okay. For example, we have learned about automatic um, swiping machine, ATM card machine, right? So we have to put the ATM card in a particular time and we have to type the password within the deadline, within the time. If you are not typing the password within the stipulated time, what happens? The card, it may come out or it may be the time, it will be, the sequence will be time out. Okay. So it is very important in real-time application to run a task within a set of time. Also, there are some tasks which is not fully dependent upon time. Okay, so even you say the same example, ATM card machines, even when it is time out, you can once again you can insert the card and type the password. It is not going to affect you. But in some cases like uh, launching launching a particular shuttle, or it may be an electronic medical supporting system or something. It depends upon the task. If the task is not properly handled within the set of time, it may cause severe damages to the environment and to the persons. The persons can be affected and also the system can also be damaged. Okay, so now you see what is process. A process is a single execution of a program. Okay, a process is a single execution of a program. So that means whatever the task you have, all the tasks are executed in a single execution. Okay, so like what we were discussing in the yesterday's example of 7-segment display. So how many character you are displaying, how much character you display, all the characters are executed in the same time. Character A, character B, C, D, what, how many characters you give, all the characters are executed in the same instant of time. Or you can say that you can execute all the characters in a single execution. Okay, so that is the process. So now let us see what is multitasking. Multitasking is when one system handles more than one task at the same time. Okay, so multitasking can be achieved by using a single microcontroller and performing many tasks to that microcontroller. Okay, or you may be having a master microcontroller which is controlled, which will be controlling many slave microcontrollers. Okay, so those kind of things are called as multitasking. Like how, for example, a human, He may be having a chewing gum, and he may be walking, he may be listening to the songs, he may be sleeping. Everything he will be doing at the same time. You'll be using your mobile phones when you're watching a TV. Or you will be eating as well as you will be using your mobile phones at the same time you will be watching the TV also. So that means your own system is supporting multitasking. Okay, so similarly, the microcontroller can also support multitasking. For example, it can detect some fire. At the same time, it can display the temperature of a room. At the same time, it can open or close the door. Everything is controlled in a single system. Okay, so multitasking is a method by which multiple tasks, also known as process. So what happens actually, all the tasks are executed at the single instant of time, share common processing resources. As I say, a microcontroller, it may be a common process resource, right? The microcontroller, it also has some memory units, which is also common to all other types of sensors, PIR sensor or a relay or a fire sensor, whatever you have, everything is kept common, such as a CPU. CPU, no, what is that? It is nothing but a microprocessor. Okay, so if the same process runs at different times, imagine process means it is executing at a single execution of a program. So, but you can say if the same process runs at different times, it is nothing but two different processes are created. That means it is executing two times. Or if it is executing multiple times, then the process is said to be multiple processes. Okay, so during that period, every process has its own state, and each state includes registers and memory. So here they mentioned registers and memory, right? These registers and memory, they are common to the process. They won't be sharing some others registers and memory. They will be sharing only the processes memory. Okay, so task is a piece of work that should be done within a period of time, and a process is a single execution of time. Multitasking is what? When one system handles more than one task, and multiple processing is what? When the process runs at different interval of times, or more than two times or multiple times execution happens. It is said to be multiple process. So scheduling states of a process is the next thing. Scheduling policy defines how the processes are selected for promotion from the ready state to the running state. Every multitasking operating system elements implements some types of scheduling policy. So the scheduling states, it can be classified into three states: waiting state, ready state, as well as executing state. The executing state is also called as running state. Okay, so imagine you have a multiple states, and some states will be under waiting condition, some states will be entering the ready condition, and some states will be actually executing or running the program. Okay, so this waiting state, it depends upon the data which is executing in the running state. Okay, so as soon as this state is completed, the executing phase is completed, it will be, the waiting state will be getting the data from the execution process. Okay, so waiting will be, before waiting state, another state you have that is called as ready state. So ready state is already loaded or given priority for the next level of execution. It is just ready. The states are just loaded in the ready state. That means after finishing the execution, the next data which is entering the ready state will be going to the execution phase. Okay, so now both waiting and ready, it depends upon the data which is used by the execution phase. Okay, so after getting the data, what happens? You can see after getting the data, it will be, the waiting state will be ready. It enters the CPU ready state. So whatever the thing which is present in the waiting state will be given to the ready state. But before that, the data which is present in the ready state should be moved to the execution state. So it's a triangular movement. As soon as the execution has completed in the execution state, the data is shared between the ready as well as the waiting state. The data which is, or the task which is present in the ready state is being moved to the execution phase, and the task which is present in the waiting state is being moved to the ready state. So within this movement, what happens? The data are shared between waiting and ready, as well as waiting will be moving the data to the ready state, and the ready will be chosen to run. Okay, and also you see at the same time, when it is in ready state, it needs the data. The data is shared to the waiting state also. The waiting state will be entering the ready state. Okay, so after the execution state, the waiting state enters the ready state. Ready state will goes to the execution phase. So this is about scheduling states of a process. So the next thing is timing requirements in a process. So timing requirements in a process, it can be divided into three timings, that is initiation time, deadline, as well as release time. So initiation time, the time at which the process goes from waiting to the ready state. Okay, so initiation time is where we can see the initiation time from the previous diagram, the time at which the process goes from the waiting state. You know that it is traveling from the waiting state to the ready state. It is called as, it is generally measured from that event. Okay, and the next one is what? It is called as deadline. A deadline specifies when a computation must be finished. Okay, this is the, you are entering into a specific interval of time. Within that specified interval of time, the task should be, or the computation should be finished. The deadline for an aperiodic process. So it can be periodic process can be divided into periodic as well as aperiodic process. So periodic process is the one which depends upon, which purely depends upon the execution of the time dependent. Aperiodic is not time dependent. Okay, a deadline for an aperiodic process is generally measured from the initiation time, because that is the only reasonable time difference. So aperiodic time, it starts from where the initiation time is started. Okay, and that will be the time reference. The deadline for the periodic process may in general occur at some time other than the end of the period. Okay, so for the periodic process, the deadline is being fixed during the start of the process itself. Okay, so the next time is called as release time. The release time is the time at which the process becomes ready to execute. Okay, so you know that initiation time is the time at which the process goes from waiting to ready state. Here, from ready state to execution state is called as release time. This is not necessarily the time at which it's actually take control of the CPU and start of the run. Okay, so when we are learning about the scheduling of the process, we learned about three states: execution, waiting, as well as ready. So from waiting state to ready state is called as the initiation time, and from ready state to execution state it is called as the release time. And every period, it should be finished within a particular deadline. So deadline, it can be a periodic process deadline or periodic process deadline. A periodic process deadline is the one which is measured from the initiation time, and periodic process is the one that other than the end of the, which is measured other than the end of the period. You can see the diagram for a periodic process, like it has the release time, So release time, you know, the time at which the process becomes ready to execute. Okay, so you can see this is the process is determined as P1 and it has the deadline. It has a particular deadline in an instant of time. Okay, so after that you see periodic process initiated at start of the period. You see, so this is the diagram for period. So periodic process means it is time dependent. You see, the time for the period to complete depends upon the time of the deadline. Here you can see there is no such period because it is an aperiodic. So deadline can be finished after the initiation time. But in the periodic process, what happens? In the periodic process, it depends upon the time, the deadline. As soon as the deadline is finished, the period is also completed. Okay. And the third one, you can see the release time. When the release time happens in the periodic process, the release time happens after the initiation time. That means after waiting to the ready state, the ready state enters to the execution phase. That is the time for the periodic process. After that, so all the things, that is the initiation time as well as the release time, together it comes inside the periodic process. Okay, so the deadline along with the period is measured in periodic process. The deadline alone is measured in aperiodic process. Okay, the next thing is we are going to see an example for the time requirement. Okay, so this is discussed under a topic, an interesting topic, which is problem faced in launching the space shuttle. Okay, and you see the space shuttle. So when they are launching the space shuttle by the US space, that one is called as the first launch in the US space shuttle. Okay, so there was a software problem which delayed the first launch. Okay, so the software problem is due to the misunderstanding of the periods as well as the task, or you say the timing requirements. So during this process, no one was hurted and the launch proceeded after the computer were resetted. Okay, however, it is a great escape because the bug was very serious and unanticipated during a particular time. Okay, so it is very important for us to run a task within a particular deadline. Otherwise, in real-time systems, it will lead to very big damage to the environment. Okay, so you see the scheduling of the system. So scheduling of the system, how they scheduled the this job. The shuttle's primary control system was known as Primary Avionics Software System. This is one of the system. Okay, PAS, Primary Avionics Software System, which is called as PAS, which is used for controlling 4 computers to monitor the events. So what do you mean by the events? Events means the set of tasks only. What the event depends upon the time. With 4 machines voting to ensure the fault tolerance. They are just used for measuring the fault tolerance. Okay. So these 4 computers allowed one machine to fail while still leaving 3 operating machines to vote, such that the majority vote would still be possible to determine operating procedures. So what they are coming to say, they created a system which supports 4 computers, and all the 4 computers is doing some set of operations. Okay, so now this set of operations is used to find the tolerance of a fault. Okay, so out of these four computers, if one of the machine fails also, okay, the decision is made by getting the output of three operating machines. That is what it was actually decided. Okay, then the next thing is what? If at least two machines failed, okay, control was to be turned over to the fifth computer, which is called as backup flight control system, BFS. So keep in your mind, there are two systems, main systems. What are they? PASS as well as BFS. PASS is given to four computers to check the fault tolerance. Okay, and the fifth computer, which is called as backup flight control system, will be taking in charge when any of the two machines from the four computers fails. Okay, so that is the suggestion made by for this, for monitoring the fault tolerance in the space shuttle system. Okay, so the BFS use the same computer, okay, requirements, programming language and compiler, but it was developed by a different organization. Imagine, PASS is developed by some other organization and BFS is developed by some other different organization. Okay, than that one built in the past to ensure the methodological errors did not cause the simulation failure of both systems. Okay, the switchover from PASS to BFS was controlled by the astronauts, right? So there are two systems, PASS as well as the BFS. So both are programmed by different organizations. So now, under the normal execution of the software, BFS would listen to the operation of the PASS computer. Okay, it will be listening to the operation of the PASS computer so that it could keep track of the state of the shuttle. Okay, BFS would stop listening when it thought the PASS was compromising data fetching. Okay, this would prevent PASS failures from inadvertently destroying the states of the BFS. Okay, so now the PASS used an asynchronous priority driven software architecture. If the priority process takes too much time, the OS can skip or delay lower priority processing. Okay, so listen carefully. During the normal operation, BFS would listen to the operation of the PASS computers. When the PASS was fetching the data, the BFS will be stop listening those things, because fetching the data, it can collapse both the systems and BFS can confuse it. Okay, so now this PASS, which is used by the four computers, they are using an architecture which is asynchronous. You all know what is asynchronous. Asynchronous is independent of time. Okay, and the priority driven software architecture is like, if high priority, so you know, all the task, all the system, it can work according to the prioritization of the task. Okay, so it is the priority is the one which is determined by the programmer only. The programmer will set some kind of signals to be the higher priority and some kind of signals to be the lower priority. Okay, so the high, if the lower priority, for instance, it is taking place first, and if there are something very emergency is happening, that means the prioritization is given to the higher priority and the lower priority will be following after the higher priority task is completed. Okay, so now in this PASS system, higher priority process take too much of time. That means it will be ignoring the lower priority processing. That is what it is scheduled. Okay, so let's see about the root cause of the failure. BFS, in contrast, it used a time slot system that allocated a fixed amount of time to each process. And in the previous slide, I was saying about the PASS. PASS was using an asynchronous system and the higher priority task is given much priority, and the lower priority task is being removed when the higher priority task is executing for a long time. Okay, so now since the BFS, what happened is the BFS is monitoring the pass system, right? So now both of the systems, they are not in a right track, they are using two different tracks. So finally the BFS system is being collapsed. Okay, so as soon as the BFS system is being collapsed because of the pass system, what happened during that morning, BFS failed to synchronize itself with the primary system. Okay, and the pass system was very inconsistent and therefore stopped listening to the pass behavior. It turns out all the pass and BFS processing are related to the telemetry data. So this occurs, the problem has occurred because of inconsistent following the inconsistent way of allocating the time slots, as well as scheduling timings are not more friendly for both the systems. So finally, as a result of BFS is being confused, BFS it made a delay to initiate with the telemetry data. Okay, so this occurs because the system incorrectly calculated start time. Now the starting time is being calculated wrongly by the BFS. So what happened finally, the system has not been running in a proper time and it fails to launch. Okay, that is what this kind of damages or this missing the deadlines in a real-time operating system may actually cause damage to the environment. So the next heading is about multi-rate systems. Multi-rate is the system where the program runs at different clock rates. Okay, it won't be following a same clock rate, it will be running at different speed and at different clock rates. So multi-rate systems, it has many applications which also includes automobile engines, printers, and also cell phones. An example is described for explaining the multi-rate system. So here in your book they have explained about automobile engine requirements under the multi-rate control. Okay, so this is an engine, an example engine. You can see the parts. Okay, a simple automobile engine controller, such as an ignition controller for a basic motor engine, performs only one task. So what is the use of ignition controller? It is to initialize the starting phase of the engine. Okay, so the task performed by the ignition controller is timing the firing of a spark plug. Okay, so timing, uh, it is very important in terms of the ignition controller. So to fire the spark plug, so it is using a timing. So after the ignition controller it starts firing the spark plug, the engine it actually start doing its operation. The spark plug must be fired at a certain point in the combustion cycle. Okay, so if the spark plug is not fired in a certain point, the ignition it doesn't take place. So in order to make the ignition task, the spark plug it produces fire, right? The use of the spark plug is used to produce the fire that that should be fired in a particular angle inside the combustion cycle. Okay, so when it is burnt in the combustion cycle, what happened, the fire is being captured and the engine will start doing its operation. So here this is the simple automobile engine which was given in your book. It contains a spark plug as well as the engine controller and also the crankshaft position. Okay, so this engine controller is the one which is used by the embedded system to check about the spark plug, the inputs of the spark plug as well as the crankshaft position. Okay, so using a microcontroller, this is the microcontroller that senses the engine crankshaft position, allows the spark timing to vary with engine speed. So this engine, with the help of this engine microcontroller, the crankshaft position is being checked at every instant of time. Okay, so firing the spark plug is a periodic process. It is not a aperiodic process, because after firing the spark plug, what happens? The combustion cycle should start to work. So firing the spark plug is a periodic process but depends upon the engine operating speed. So there are two things that should be notified. As soon as the plug is being fired, it should be relating with the instant of the engine's crankshaft position. Okay, so automobile engine controllers use additional sensors including pedal position and oxygen sensors is used to control the emission. So like even for this automobile engine, it not only needs the fuel or the what is that a spark plug, it also needs some kind of oxygen to make the fire to execute the engine for a long time. Okay, so the mixture of the gas or a fuel and the oxygen, that should be in equal proportion so that the engine will be rotating in some instant of time continuously. Okay, so there are some other special sensors are used to sense the level of the oxygen and also the pedal position. All right, so now the engine controller takes a variety of inputs that determines the state of the engine. It controls two basic parameters: the spark plug fringes and the fuel air mixture proportion. So they are the two important parameters: the spark plug as well as the mixture, that should be in a proper position. Okay, the engine control is computed periodically, but the period of different inputs and outputs in several orders of magnitude of the time. Okay, so now you can see that multi-rate system is employed in this engine controller. This engine controller is the one which is used to get the data of this crankshaft position. At the same time, this should be equally managed with the spark plug for the ignition to begin. So as soon as the ignition is begun with the help of the spark plug, it should be loaded to the crankshaft by means of the combustion cycle. And also when you are doing this, the oxygen level as well as the spark plug ratio, that should be maintained carefully. Okay, so everything is sensed by means of the engine controller. So engine controller is the one which is sensing the oxygen sensor as well as the spark as well as the crankshaft position. Okay, so that is what we call it as multi-rate systems. So another example of multi-rate system, you can see your microcontroller which is supporting different sensors. It may be a fire sensor or maybe a temperature sensor. All the quantity of the sensors are sensed, and some kind of relay activities can also be managed with the help of the sensors. So that kind of systems are called as multi-rate systems. So that's all about part 1. So revision questions can be given at the end of unit 4. Thank you.